Hello everyone, it's really my honor here to have the presentation and share my work with you. So we will start. Let's start now. The topic of my work is error sound sampling and characterization techniques using time grid. In this presentation, there are 4 parts. The first part is the background and objective, which include the definition, sources, and effects of airborne particles, and also a developed MPS sampling system. Regarding to the MPS sampling system, there are still some problems need to be solved. So next, I will introduce the problems and the research objectives. The second part is the time grid sampling efficiency. It is a development of the MPS sampling system, which include the theoretical and experimental sampling efficiency, and the improvement of the time grid sampling efficiency, and the quantification of the time grid sampling efficiency. And then, based on the development of the MPS sampling system, we proposed a mass quantification method, which includes the reference particle deposition on the time grid and the correlation of reference particles and unknown particles. The last part, of course, is the conclusions. So now we start with the first part. In 1952, a big smoke in London has been paid much attention to. This crisis causes about 12,000 deaths. Since then, people start to realize the importance and the impact of the aerosol. So what is aerosol? Aerosol is a suspension system of solid or liquid particles in a gas. The gas is normally the air. Actually, there are many kinds of aerosols. The natural aerosols, for example, the fog, mist, dust, and diesel steams. And also, there are many kinds of anthropogenic aerosols, for example, the smoke, the combustions, the exhaust of cars, and also the microbial aerosols. Actually, with the particle size smaller, they are much easier to enter in human body. And this part of 5 particles are relatively complicated to analyze. So our work focuses on the submicronic particles, especially the nanoparticles. There are many sources of these parts of the 5 particles. For example, mining, combustion, auto traffic, which may release the 5 metal and metal oxide particles, the carbon particles, carbon black, carbon nanotubes, and other kinds. Especially for the auto traffic, not only the exhaust of the cars, the other parts of the cars, for example, the gear, may also release different kinds of the 5 particles, for example, the 5 carbon particles. And besides these sources, the nanotechnologies, as we know, has been used in many applications nowadays. The medicine, the energy generation, the laundry, and so on. For example, the gold nanoparticles has a good high light to heat conversion capability, which is a good photothermal therapy to kill the cancer cells. But turning on of this process, the 5 particles, especially the nanoparticles, may be released to the environment. After these particles released to the environment, they may be inhaled by the human and accumulate on the brain, lungs, heart, and skin and other organs, which may cause damages and diseases. Besides the effect on the human body, these particles may also do harm to the ecosystem. For example, the titanium dioxide nanoparticles is a really good photocatalyst. But if they are illuminated by the sunlight, they can catalyze the chemical reaction to increase the concentration of ROS. As we all know, ROS will do harm to the organisms such as small fishes. So the sampling, measurement, and the characterization of the airborne particles is very important. Nowadays, there are many methods for the particle sampling, but among them, the mini particle sampler is a really low-cost, portable, and easy-to-use one, as we can see from the figure. It is really small and we can very easy to use it. The time grids can be directly installed inside the MPS, and it consists of a copper mesh and a carbon film. Using the MPS, the sampling time can be down to a few minutes, and we don't need any difficult sample preparation for time analysis because the time grid is directly installed inside the MPS. We can take many different types of time analysis and get the physical, chemical, individual particle information. This technique has already been used in many applications. For this kind of the sampling technique, the sampling efficiency, of course, is a really important parameter to care about. Mili has already compared the experimental and theoretical method sampling efficiency, but in his work, the used models were not well chosen, and the minimum efficiency is 15%, which need to be improved. Besides, the collection implies uncertainties which need to be quantified. Then, using this technique, we can get the different kinds of information, for example, the particle size, shape, number, and composition, using the time and EDS. However, this technique is not specific for mass characterization, so we want to propose a new mass characterization method. Here we come to our 4 main objectives, which include the first one is the study of filtration mechanisms involved in the MPS sampling and the comparison of the theoretical models. The second is the improvement of the time grid sampling efficiency. The third one is the development of the quantification method for the time grid sampling efficiency. The last objective, of course, is to develop a new quantitative method to characterize the mass of contaminant. So here we come to the part 2. First, I will give you the definitions of the theoretical and experimental sampling efficiency. Many models have been proposed to simulating the sampling efficiency. We have explored and concluded on the available models for the different types of sampling conditions, which has been shown in the paper below. But here, I will only introduce those models fitting for our sampling conditions. The capillary pore model can be used for the simulation. As I introduced before, the time grid consists of a copper mesh and a carbon film. But according to Oguha, the sampling efficiency of copper mesh can be ignored because the pore size of the copper mesh is much bigger than that of the carbon film. So we can only focus on carbon film. The particles can be captured by the carbon film by different individual filtration mechanisms. The small particles are preferred to be captured by the diffusion on the pore surface, EDS, and also the diffusion on the pore wall, EDW. But the big particles are preferred to be captured by the impaction, EI, and the interception, ER. The overall sampling efficiency can be calculated according to the individual sampling mechanisms. And Maiqi has proposed another kind of model which compares the interception efficiency ER and the diffusion efficiency on the pore 1 EDW to pore 1 capturing EDR. So here we get 2 forms of the overall sampling efficiency. In Mili's work, the diffusion efficiency due to pore 1 has not been involved. Besides, the diffusion efficiency due to pore surface is only fit for the fibrous filter, not for our nuclear pore filters. And at last, because our flow velocity is relatively high, so the flow slip cannot be ignored, especially for the pore 1 capturing. Using our improved models, we found that there are consistencies between the theoretical sampling efficiency and the experimental sampling efficiency. And the second model performs a little bit better. After the definition of the theoretical sampling efficiency, I want to introduce you the setup of the experimental sampling efficiency. At first, the poly-dispersed particles are generated from the atomizer, which filled with the salt solution. And then, two jars are used to remove the water drops. Then the particles enter into the classifier. The extra flow go out from the filter. In the classifier, especially in the DMA, the mono-dispersed particles are generated. A neutralizer is used to neutralize the particles, and the MPS, of course, is used to capturing the particles. At last, a CPC is used to measure the particle number on particle number concentration. For our setup, the most important part is focus on the classifier. Especially in the DMA, the mono-dispersed particles are generated from the poly-dispersed particles. So we will introduce how it works. The classifier includes an impactor, a neutralizer, and a DMA. In the impactor, big particles are removed. And then we use a neutralizer. The particles are positively or negatively charged. Then the charged particles enter into the DMA. In the DMA, we can choose either positive or negative charge on the high voltage route. So there is an electric field inside. The charged particles will move, and the particles with the specific electric mobility can go out from the DMA. And we know there is a relationship between the electric mobility and the particle size. So that means only the particles with a specific size can go out to the DMA. That means we can get the mono-dispersed particles. The sampling efficiency was checked by the 3 steps method. The first step is measurement without time grid. We can get the particle concentration upstream. And the second step is measurement with time grid. We can get the particle concentration downstream, of course. And the last step is to check the stability of the setup. And then the sampling efficiency and the particle deposition number can be calculated according to the particle number on particle number concentration which measured by CPC. After the definition of the theoretical and the experimental sampling efficiency, lots of tests have been carried out. What's the good thing is for all our sampling conditions, the fixed model is always proper. So there are 2 kinds of parameters involved in the models. The first type is variable parameters. They include the filter pore size and porosity, the flow rate, the particle density, and the temperature. And the other type is constant parameters, which includes the filter thickness, the Boltzmann constant, the viscosity, the slip lash, and also the Cunningham convection factor. Here we take an example of sampling the sodium chloride using 1.2, 1.3 time grid at a flow rate of 0.6 liter per minute and a 300 K temperature. Results show that there is a consistency between the theoretical sampling efficiency and the experimental sampling efficiency. The small particles are mostly captured by the diffusion mechanisms, and the big particles are most preferred to be captured by the impaction mechanisms. For the particles with size between the 10 nanometer and 100 nanometer, the mechanisms by the capturing mechanism by the power is weak because the filter's thickness is only 0.02 micrometer. Here I want to explain that the 1.2, 1.3 time grid means a time grid with a pore size of 1.2 micrometer and 1.3 and a pore pitch of 1.3 micrometer. The porosity can be calculated according to the pore size and pore pitch. So we come to the second part, how to improve the time grid collection efficiency. We have investigated on the influence factors. There are many influence factors involved in the setup. For example, the first one is the set concentration, which may change the generated particle number and may have an influence on the sampling efficiency. And then is the electrical charge. We can choose positive and negative charge, but this electrical charge may change the electrical mobility, so maybe have an influence on the sampling efficiency. Next factor is the measurement method. The method 1 is we use in our work, but method 2 is always being used by many people. So we want to compare if there is some difference when we use different methods. Besides these parameters only involved in the setup, we have also many other factors not only involved in the setup, but also involved in the theoretical models. We want to compare if there is a difference between these two kinds of parameters. So we take a test using different kinds of flow rates, 0.4 and 0.6 liter per minute. The particle diameter has been fixed as 10 and 100 nanometer. The Dikegiatan method is used to design the experiments. It reduces the experiment cost to only 12 tests. And using the Dikegiatan method, we can figure out which factors are significant. We can also get the best parameter combinations of control factors. The results show that the flow rate and the particle diameter a big significant influence on the sampling efficiency because the p-value is smaller than 0.1. And the 0.6 liter per minute flow rate has a higher SN ratio. This means it has a higher sampling efficiency than the 0.4 liter per minute. So, and the 100 nanometer particles forms a higher sampling efficiency than the 10 nanometer particles. We can induce that only the parameters involved in the theoretical models have a significant influences on the sampling efficiency. So we will focus on the variable parameters involved in the theoretical models, which are filter pore size and porosity, flow rate, particle density, and the temperature. First is the pore size. We use different filters with the pore size of 0.6 micrometer and 1 micrometer. The results show that with the pore size smaller, the sampling efficiency is higher. That's because a smaller pore size filter will increase the diffusion efficiency and also the impaction efficiency. Now, when we use different types of filters with different porosity, we thought there is a minor influence. And for the flow rate, we use 0.4 and 0.6 liter per minute. The Milli's results has also been compared. He used a 0.3 liter per minute flow rate. The results show that with the flow rate higher, the minimum efficiency is higher, and the particle size corresponding to the minimum efficiency is smaller. That's because with a higher flow rate will increase the impaction efficiency, which mainly function to the big particles. With sampling sodium chloride and cesium chloride to check the influence of the particle type on the sampling efficiency. And for that, using denser particles, the sampling efficiency is higher. That's because the denser particles will also increase the impaction efficiency. When we increase the temperature from 290 to 300 K, we found there is a minor difference. So that means we can improve the 15% of sampling efficiency to 40% sampling efficiency by using a small pore size filter and a higher flow rate, and also use denser particles. After the improvement of the time-grid collection efficiency, here is the third part is the quantification of the time-grid collection efficiency. There are many parameters involved in the theoretical models, as I introduced before. But all of these parameters are the sources of uncertainties. Each parameter has been modeled as a distribution, and the combined uncertainties can be propagated by the individual uncertainty. Besides the theoretical uncertainty, we also talked about the experimental uncertainty because the particle number or particle number concentration measured by CCPC is fluctuant. So we checked the uncertainty from the experimental. Here we take an example of sampling the sodium chloride using a 1.2, 1.3 time grid at a flow rate of 0.6 liter per minute and a temperature of 300 K. The gray part means the theoretical uncertainty, and the EXP means the uncertainty from the experimental dispersion calibration, which are also carried out by the Monte-Carlo method. The result shows that the uncertainties from the measured data are mostly covered by the reach from the models, and the theoretical uncertainties is between 5% and 9%. The experimental uncertainties is normally smaller than 1%. We can see for the 5 nanometer particles, the uncertainty is relatively high. That is because the number concentration is too low to be constant, and the 5 nanometer is the detection limit of the CPC. So that shows a relatively high uncertainty. The sensitivity of the parameters involved in the theoretical models have already been also being checked using the Sobel sensitivity analysis. Different particles with different sizes were checked, and when the EDs is larger than 0.1, we can see that this parameter brings big uncertainty to the sampling efficiency uncertainty. The result shows that the pulses always bring the biggest uncertainty to the sampling efficiency uncertainty. And for the small particles, the CC is also a great uncertainty because of the use of the different coefficient turning the CC calculation. For the big particles with big size, the flow rate becomes a big source of the uncertainties. We have also checked in other sampling conditions when we have changed the pore size, changed the flow rate, and used different height of particle to check to do the uncertainty analysis. The results always show that the uncertainty from the measured data are mostly covered by the reach from models, and the theoretical uncertainty are mostly smaller than 10%, and the experimental uncertainty is normally smaller than 1%. So here we have well development of the sampling system. Based on this well development of the sampling system, we proposed a new mass quantification method using the time EDS. The main principle is to deposit the unknown particles on one time grid, and then we add a quantified reference particles on the same time grid. Using EDS, we can know the mass ratio of the elements involved in the unknown aerosols and the elements involved in the reference particles. And combining the mass ratio and the mass of the reference element, we can calculate the mass of any element in the unknown aerosol. For this method, we have two main problems. The first problem is how to deposit quantified reference particles on the time grid. The second problem is how we can know the mass ratio measured by EDS is the right one. So we will firstly solve the first problem, how to deposit quantified reference particles on the time grid. The mass of the reference element is a function of the reference particle diameter and the particle number. The particle diameter can be controlled by the classifier, especially, of course, by the DMA, and the particle number can be controlled by the CPC. Here we have 4 requirements for the quantification definition. The first one is feasibility. We need to deposit enough particles to compare with the unknown particles. The second one is reliability. In this part, we will analyze by the time. And then the third one is the repeatability of the deposition, and the last one is the stability of the setup. The candidate reference particles are rubidium chloride, cesium chloride, strontium chloride, gallium nitrate. Because the elements involved in these particles are not common in the ambient air. Here, the sodium chloride is used only for the tests. Here is the first requirement, is how to deposit enough particles. Here we need the sampling efficiency is the highest and the number of deposited particles per minute is the most. For sampling efficiency, we have discussed in the part 2. The sampling conditions is 1.2, 1.3 type grade, 300K, 0.6 liter per minute, and sampling denser particles and the diameter prefer to be 60 and 100 nanometer. For the goods, we have checked the number of depositing particles per minute in these different kinds of sampling condition. The really good result is that in the same sampling conditions, not only the sampling efficiency is the highest, the number of depositing particles per minute is also the most. But besides these parameters involved in the sampling efficiency, the salt concentration may also have influence on the particle number, deposited particle number. So we have checked the relationship between the salt concentration and the depositing particle number. The result shows that with the salt concentration higher, the number of depositing particles per minute is also higher. But there is a limit, so we can choose a relatively high salt concentration to get our goal, feasibility. The second requirement is the reliability. We use time to do a comparison. The time images shows the particles are mostly homogeneously distributed on the time grid, and the size observed by the time is similar to the size selected by the DMA. Now, what's important is the particle number observed by time is also similar to the number measured by CPC. Besides the particle size, the particle shape also may bring errors. So we have checked the shapes of the different kinds of particles. We can say that for the rubidium chloride and cesium chloride, when they are in the smaller size, for example 60 nanometer, they prefer to be physical. But when they are in the big size, for example 100 nanometer, they prefer to be cubic. It's strange. But for our situations, we prefer to have physical particles because there will be minor difference between the electrical mobility diameter and the diameter measured by observed by the time. So the 60 nanometer rubidium and cesium chloride will be good references. For the strontium chloride, the shape are not clear. They are hygroscopic. And so for the gallium nitrate, they are hundreds. So we will keep use the 60 nanometer rubidium chloride and cesium chloride to get our goal reliability. The third one is the repeatability. For different sampling conditions, different repetitions have been carried out. The result shows that the particle number upstream, particle number downstream, the deposited particle number, and the collection efficiency are more or less stable, especially for the particle deposition number and the sampling efficiency. So we can say we can get the repeatability turning the different definitions. We also checked the variations of particle number with time. 3 repetitions of rubidium chloride sampling and 1 cesium chloride sampling were carried out. The results show that even if there is a little difference between the different repetitions, but for one sampling, the particle number with sampling without time grid and with time grid are more or less constant. The linear fitting has been carried out. We found that there are two kinds of R value in the results. The first R value is there is no R value. That means the y-axis, that means the particle number per second didn't change. That means the particle number is stable. And the second R value is bigger than 0.9. That means there is a linear correlation between the particle number per second and time. So we can average the values from step 1 and step 3 to decrease the error. In this way, we can also achieve the requirement stability. So here we have achieved the 4 requirements to deposit quantified reference particles on the time grid. So we come to the problem 2. How we can know the mass ratio measured by EDS is the right one. Here we need to deposit two kinds of particles on one time grid, the reference particles and unknown particles. We want to know the mass ratio. But in order to know the mass ratio measured by EDS is the right one on the not good one, firstly we deposit a reference particles and a pseudo unknown particles on one time grid. In this way, we can get the experimental mass ratio measured by EDS, and we can also know the theoretical mass ratio. In this way, we can do a comparison and know if the EDS value is the right one. Here we take an example of rubidium chloride and cesium chloride deposition. 21 squares with uniform spaces were carried out. The STEM images show that the particles didn't change after turning the 15 minutes mapping, and the rubidium chloride and cesium chloride are uniformly distributed on the time grid. For the square 8, we found that the mass ratio between the rubidium and cesium is 33 to 67. And for all the 21 squares analysis, we get a mean value of the mean mass ratio of rubidium and cesium is 46 to 54, with a standard deviation smaller than 8%. In this situation, the theoretical mass ratio is 38 to 62. That means the absolute deviation is 8%. Similar tests have been carried out. We found that the absolute deviation is always smaller than 9%. So we can see when we deposit reference particles and pseudo unknown particles, there is a consistency between the theoretical mass ratio and the experimental mass ratio. Besides to deposit reference particles and pseudo unknown particles, we also deposit reference particles and real unknown particles. That is rubidium chloride, and the unknown particles is the breaking particles. From STEM images, we can see that the rubidium chloride is always uniformly distributed on the time grid, and the time grid is full of the element carbon and copper, because the time grid consists of a copper mesh, and the carbon film. So the breaking particles, we can get that the breaking particles consist of the element error and element oxide. But the element oxide is a really light element, which is not easy to be analyzed by EDS. So here, using this method, we will only focus on the element error. For the 21 square check, we can get a mean mass ratio between the element error and rubidium is 92 to 8. And the standard deviation is smaller than 5%. Now we can get the mass of the error on the grid And we can also get the mass concentration or error in the breaking error zones. These are the very important information we want to get. Besides the mass ratio detected by the EDS, we also estimated the theoretical mass ratio of element error and rubidium to have a comparison. The size distribution of breaking particles are characterized by SMPS and APS. Compare the size distribution, the pore size, the porosity of filters, and the flow rate, the density. We can estimate the time-grid sampling efficiency. And then we can get the mean estimated mass ratio between the element error and the rubidium is 98 to 2. The absolute deviation is 6%. That means there is again we have a consistency between the estimated theoretical sampling efficiency, the mass ratio and the mass ratio measured by EDS. That means the mass ratio we get from the EDS is the right one. So the problem 2 solved. So here we come to the conclusion part. First is the development of the sampling system. There is a consistency between the theoretical and the experimental sampling efficiency. And then we have improved and quantified the sampling efficiency. To increase the sampling efficiency, we need to use denser particles, 1.2, 1.3 time grades, 0.6 liter per minute flow rate, and also use the particle diameter within the 60 and 100 nanometer. For decreasing the uncertainty, we need to control the pore size of the filter and also the flow rate. Based on the development of the sampling system, we deposit the reference particles on the time grid. We want to deposit quantified reference particles, and we have achieved the 4 requirements: feasibility, reliability, repeatability, stability. So that means we can deposit quantified reference particles. And then we deposit 2 kinds of particles on one time grid. The one kind of particles is the reference particles. Another kind is unknown or pseudo-unknown particles on one time grid. Rubidium is always a good reference because of these reasons. First, it is stable and not common in the ambient air, and it has low toxicity. It is no hygroscopic, no hydrated, and turning the EDS analysis, only a few peaks performed, and the 60 nanometer rubidium chloride is physical. For all the situation, the deviation between the theoretical mass ratio and the experimental mass ratio measured by EDS, there is a consistency. So we can say the mass ratio measured by EDS is the right one. That means the method is good. Our method can easily to be used for mass quantification. That's all. Thank you for your attention.
Thank you, Maiqi, and what a great presentation you have done. And we would continue with some questions. We already have some, I think, somebody typing in here. And if everybody want to ask directly to Maiqi, please raise your hand. You can ask directly. But before we can start with this, the first one, is the type of fluid flow contribute significantly? Yeah, it means if the fluid flow is turbulent or laminar, is it yeah, I think it's the question. Will impact it the...
Hello, Michael?
Yeah?
Hello?
Yeah, hello?
Oh, okay.
Would you hear me?
Yes, I can hear you.
Yeah, the question is, I want to ask that here in the chat box, is the type of fluid flow contribute significantly to your measurement? Is it if the fluid flow is turbulent or laminar, something like that?
I'm checking the chat box.
Okay.
Is the type of fluid flow contribute? Yes, of course. For the series, this part we care about this part for the models because when we sampling the particles, the flow, the type of the flow, and many other factors will influence the sampling efficiency. The models actually the filter we used is the nuclear filters, but for this type of filters, when the flow is a laminar on the I think it's a turbulent flow, the models are different. So when we choose the models, we need to according to our sampling conditions. For our situation, because the flow rate is relatively high, it's more than 1 meter per second. So the flow is a laminar flow. So we only can choose the models fit for this kind of sampling conditions. That's why I say that the models used in the RMILI, which published before, is there is some not mistakes, some places not very good. So we have improved the models and use proper models. Of course it has impactions.
Okay, and we have, I think the second one, this was from Miss Erlina. She is our great lecturer in our university. Her question is, thank you for your great research. Your presentation is very interesting and comprehensive, and it's discussion as well. I have two questions for your presentation. The first one, what can we do so that the particles do not agglomerate again? The first one, when it's moving. And the second one, have you confirmed comparing the particle size results using them with particle size analyzer?
It's the first question. Thank you for your question. It's a really good question, interesting question for the first one. And for our the sampling efficiency test, we use the monodispersed particles, because if we use the agglomerate particles, the process will be really difficult. But in our application for the new mass characterization method, we need to sample at first the unknown particles, and then we deposit the reference particles. Of course, reference particles are always monodispersed, but the unknown particles we can't control it. But the really good thing is we only focus on the mass, the particle mass. So we don't care about the particles if they are monodispersed or agglomerate. But we care about the mass. The mass is always the same. So that is one advantage of our method for the mass characterization. And the second one is to confirm.
Comparing the particle size result with PSA, particle size analyzer. Not only by TEM, but did you make other comparisons?
Actually, the results of the size distribution, the results of the size distribution is from PSA. It's not my results. So I think it's real ones. Yeah.
Okay, thank you. If you have other questions, please type or you can ask directly. Okay, thank you, Miss Erlina. And actually we have another one. Is the system could recognize the shape of the particles? I think your presentation already addressed this. But maybe if we can extend it further, is it? I seen that the shape you presented is spherical and cubic.
Yes.
Other types, maybe for cylindrical or something like that, or arbitrary shape that we can know, because if in the application in the real life when we breathe, everything particle in every shape.
Yes.
How about this?
Yes, there are always two kinds of particles. For our situation, with the unknown particles and the reference particles. For reference particles, we need to choose a really good one. as I introduced before, the spherical type and the particles with a really clean shape. But for the unknown particles, we can't control. The same reason is we don't care about that. We only care about the mass. So this problem is not a problem.
Yeah. Okay. Okay, and I have wondering just one question more for me in terms of this application is for filter, right?
Yes.
Filtering something and
yes, to sampling to collect the particles.
Yeah, and I see a lot of application, especially due to the COVID pandemic. So everybody is care about the air quality, indoor air quality is a lot of about thing, and they work especially in filter as well. And I just wondering if the filter is used, do we can determine how long it can last? For example, what is the parameter that influence, for example, the what is called the time, the duration.
Sampling time.
Yeah.
The sampling time. The one advantage of this sampling system is we can sample really a really short time. It can be done to a few minutes, but it depends the applications. For example, we need for example for our application for the mass characterization, we were to deposit some unknown particles. We have a mass comparison, so we don't need a very long time deposition. If we use sampling too long time, there will be much more the unknown particles. In this way, we need to deposit really long time reference particles to compare with the unknown particles. So we don't advise to deposit really long time. So I have another thing to want to say is to introduce our new method. It is really convenient. You know, for the normal situations, when we want to know the mass concentration of the particles, we always needed a very big very heavy instrument in the sampling pot. But using our method, we only need to use the MPI sampling system. As you can see, it's only really small and very easy to use. And in the sampling pot, it's really easy to collect the particles, and then we can only do a simple MEDS analysis in the lab. We can get the particle size, particle information, for example, the size, the shape, the number, and the mass. So it is really, I think, advantage of our methods. I want to add.
Yeah, you did a really great research and job. And yeah, do we have any question for the participants? Yeah, I think we also almost running out of our time. So we want to thank you again, Maiqi, for your contribution and your sharing time, especially for us. I'm so sorry because I changed the date.
It's okay. It's okay.
And we have a certificate. I will send you to your email. This is.
Thank you so much.
This is from our head of international office in my university. We call it Untirta. And if you have time to visit Indonesia, please come.
Thank you. Thank you for inviting me.
Yeah, have you here. And Dr. Maiqi, on the behalf of our university, we would say thank you again. And we wish the best for your next career. We don't know yet. Yeah, I hope you are in academics, so we can work further or in any field. So we can work further. And it's really enjoy to talk with you today. And yeah, wish you all the best. And thank you for all the participants. We can give applause to our below speaker, and we see you again in another research talk, in another topic. So yeah, we really love to meet you again in another occasion, Maiqi. Okay.
Thank you so much.
Thank you so much, Maiqi. See you.
See you.
Enjoy your holidays. Thanks so much.
Thank you everyone. Thank you for sharing.
Thank you.